talking about area and something called the definite integral. Now, the big idea in this chapter is this idea of, we want to talk about finding area. So we might ask a question like, find the area under y equals x squared between x equals 0 and x is equal to 1. All right, so in the very beginning of calculus, the big question that we were asking was, how fast is the boy raising the flag? Or how fast is the flag being raised? So how fast was the question that we were asking. How steep, how steep, how fast, that kind of question. Okay. Now the question we're asking is, we want to talk about finding area. Now, y equals x squared, I know what that looks like. That's a parabola. Looks something like this. And if I want to find the area under y equals x squared between x equals 0 and x is equal to 1, then what I mean by that, even though I'm using the word under, the real meaning of that is I'm finding the area under this curve y equals x squared but above the x-axis. So I'm talking about the area between or below y equals x squared and above the x-axis. So that's the area that we're trying to find. Now, if what we had there was not a parabola, if what we had was a diagonal line, straight up along here, we have a shape that was a triangle, and I know the area of a triangle, that's 1/2 the base times the height. Or if this was shaped where it looked like part of a circle, I know the formula for the area of a circle, and so I could use that to figure out the area of this shape. But if you look in the front of your textbook, or probably in the front of most textbooks, there is not a formula to find the area of this shape, the shape under a parabola and above a straight line. Okay? And so our goal today is to come up with a way to find that area. Okay, any questions about that so far? Okay? All right. So, we don't have a formula for an area of this shape, so we've got to come up with another idea. Okay, so here's an option, and there are actually many, many options that are totally legitimate as ideas for coming up with the shape of this area. I'm going to tell you about one idea, and the reason I'm going to tell you about this idea is that this idea is going to get better and better, kind of like Nintendo. So here's the idea. Here's our option, an option. Our option is that we're going to take this picture that I have, and we're going to break up this interval from 0 to 1 into a couple little subintervals. So here I've got a really skinny one, and then a fat one, and then maybe another one over there. Okay, so I've broken up the bottom of the interval into 4 different pieces. And so what I'm going to do is, over this interval that I'm looking at, over this one interval that I'm looking at, instead of looking at the top of my function as something that is changing from the left over to the right-hand side of this curve, I'm going to pretend that this curve is flat. There it is. Flat all the way across. So, over our subinterval, we'll pretend that our function is constant, meaning flat. And I'm going to do the same over each of my other intervals as well. So wherever, I'm just going to say, all right, so that's about maybe the middle. There we go. And so what I'm doing here is that instead of having some curved function like y equals x squared, I have a bunch of level flat places along here. And so when I do this, then I can find the areas of each of these rectangles. Area of a rectangle is length times, or base times height. And I find the area of those rectangles, and I'm kind of finding the area under our curve. So over the subinterval, we'll pretend that our function is constant. And then we'll find the areas of each of these rectangles. Then use that information. We're going to use that information to approximate the area under y equals x squared. Okay. So this is kind of our 4-bit graphics right here, right? I mean, we've got these flat spots, but really it's supposed to be a nice smooth curve that we've got here. So you might see where this is starting to go. Right now I have 4 intervals, and they're not even split up evenly. So maybe the first thing I'll do here is to make this a little bit more more uniform. So to move forward, we'll break our interval into equally spaced subintervals. So in keeping with the idea of 4-bit graphics, let's break this interval from 0 to 1 into 4 equally spaced subintervals. So if I break this picture up, the interval from 0 to 1, into 4 equally spaced subintervals, then I have some labels on these marks here. So what I'd like you to do right now is to take a look at your neighbor and tell your neighbor what these marks should be in between 0 and 1 so that these are equally spaced subdivisions.
We're breaking the 4 into 4
We don't know that.
Exactly sure.
Oh, it's 16, right?
Yeah.
Okay.
All right, so you've got some numbers down there. Okay, so you copy your numbers down, that's all right.
Plus 1. And if they're wrong, Steve told me.
All right, so we're going to blame this on Steve if they're incorrect.
Thank you.
Okay, so at least one person believes that these interval marks should be 1/4, 1/2, and 3/4. Does anybody else agree with that? Okay, so this seems pretty reasonable. Okay, so I took my interval from 0 to 1, and I split it. I divided that interval by 4, and so each interval will be a length of 1/4. All right. So once I have this, again, I'm trying to approximate the area between 0 and 1 under y equals x squared. The other thing that I want to do to make my life a little bit more uniform is over here, I just kind of randomly made a flat spot somewhere along that interval, and that flat spot touched the curve somewhere within that subinterval. To make my life uniform and a little bit easier to deal with, I am going to choose for all my rectangles to touch the function on the upper right corner. So on the right corner of the rectangle. So what that means is on this first interval here from 0 to 0.25, I am going to go over here on the right side and draw a line straight up until I hit the function, and then draw a horizontal line over to the left, and then down. And then I'm going to do the same thing at 0.5. Straight up to my function. That right-hand corner is touching the function, and then I'm going to pretend that my function is flat over to my next subinterval mark. And I'm going to keep doing this all the way across, and I should end up with 4 rectangles. And my last one should be over here on the right. So each rectangle is touching the function on the upper right-hand corner of the rectangle. All right, are there any questions about that picture? Okay. So if we wanted to do some number crunching, and we do, if we wanted to do some number crunching here and use these rectangles, our Atari 2600 version of the area, well, then what we need to do is find the area of each of these rectangles. So the area of each rectangle, well, I've got 4 rectangles, so I'll call them 1, 2, 3, and 4. So for rectangle 1, I've got area of the base times the height, so length of the base times the height gives me the area of that first rectangle. And so the base is a width of 0.25. How do I figure out the height of this rectangle?
F of x.
Okay, so yeah, the height of this rectangle here depends on the curve, and in particular, the right-hand corner is touching the function. So I need to know what the height of the function is right here at 0.25. So it's 0.25 times f of 0.25. Now our function is y equals f of x, which is x squared. So f of x equals x squared, which means in our case we've got 0.25 times 0.25 squared. So if you have your calculator, please pull it out. This is definitely a calculator active part. So please pull it out and crunch this number and see what you get. Compare it with your neighbor.
Whoa. All right. You got it. Yeah, Lon got it. 0.015625. 25 gauge.
All right, can you repeat that number one more time, please?
0.156. 25.
25. Okay, do I have a second on that number?
Yes.
Awesome. Okay, so we now have the area of rectangle 1. Now we need to figure out the areas of rectangles 2, 3, and 4. Okay, so for rectangle 2,
Oh, wow, I didn't even know.
well, rectangle 2, our length of our base is the same. The width is still 0.25.
No, it is blood.
And the height of this rectangle, well, that depends on this upper right-hand corner, which lives on the function when x is equal to 0.5. So we've got f of 0.5. So our numbers will be 0.5 times, I'm sorry, 0.25 times 0.5 squared. All right. Are there any questions about this part right here? Ben, are you okay?
Huh? Yeah, I'm fine.
Okay. Okay, so we need a number for this. Did anybody crunch that number out?
0.0625.
0.0625. Do I have a second on that number? Second on that? Okay, 0.0625. So now we have 2 more rectangles, which means that this half of the room, all 5 of you, are in charge of rectangle 3. And everybody else is in charge of calculating the area of rectangle 4.
That was a tough one.
That was a very tough one.
Very hard.
Alright. What is that?
Yeah, I'm making it tough.
So we now have areas for all four of our rectangles. Are there any questions on coming up with those areas? Okay, so now we can approximate the area under our curve. And so the area under f of x equals x squared between x equals 0 and x equals 1 is approximately, well, I'm going to have to add up the areas of all of these, so it's approximately 0.015625 plus 0.0625 plus 0.140625 plus 0.025, and if you add all those numbers together, what do you end up with? 0.
No.
No.
Left.
Yeah,
Oh.
It's 0.46875.
Okay, can you say that again?
46875.
46875.
Yes.
Okay, do I have a second on that number?
Yes.
Yeah, great. Okay. So, what we have just figured out is that if we own an Atari 2600, then we can approximate the area under y equals x squared by making 4 rectangles with right-hand corners, and when we add the areas of those rectangles, we get 0.46875, and so that's an area, and so this would be square units. All right, any questions about that? Okay. So something that you might notice about this picture here is that every single one of our rectangles in this particular example stuck out over our function. Okay, and so we were really over-approximating by all of these sort of semi-triangular areas, and so the value that we came up with is certainly larger than the true area. Now, we made 2 choices in this case. One choice was that we chose exactly 4 subintervals. We broke the interval from 0 to 1 up into 4 equal pieces. And the other choice that we made was that every single rectangle would hit the function on the right-hand corner. So if I did a similar idea where I still had 4 subintervals, but instead I had the corner on the left-hand corner touching my function, then I'm going to get a slightly different picture. So 4 subintervals, but have the left corner of the rectangle touch the function y equals f of x. So if I do that, I still am going to break this 0 to 1 up into 0.25, 0.5, and 0.75. But now, when I draw my rectangles, each rectangle is going to touch the function on the left-hand corner. So in this last subinterval over here from 0.75 to 1, I'll start at 0.75 and draw my rectangle straight up to the function and then straight across. So that's my first rectangle touching the function on the left-hand corner. And then my second one. And my third one. Now my very last rectangle is kind of a funny one, right? Because on this the interval from 0 to 0.25, well, the left-hand corner actually is right where the function is touching the x-axis. So my last rectangle here actually has an area of 0. Okay, so here's my picture. I now have 4 rectangles. One of them is kind of what's called a degenerate rectangle because it's totally smushed down and there's no height to it, but it's still technically a rectangle, just a little funny looking. Okay. And so I've got these 4 rectangles, and so my approximate area well, I can write out each of my rectangles separately, or I can think about this as writing this all out as one big sum. So my first rectangle here, the width is 0.25, and my height is f of 0, because I'm plugging in the x value in the left-hand corner of the rectangle. Plus, I've got the width of the rectangle of 0.25, and the height for my second rectangle, that's f of 0.25. And my third rectangle, width is the same. And my height is f of 0.5 on my third one. And my very last rectangle, my width is 0.25 and my height is f of 0.75. So symbolically, I'm writing down the areas of all 4 rectangles all together rather than writing each of them separately and then adding them together. Okay. So now I've got this approximate area. We've got 0.25 times f of 0, which is 0. We've got 0.25 times f of 0.25. And that one, we can either recalculate it. Remember, f of 0.25 is 0.25 squared in this example. And you can double check that, but it should be this number right here. So we've got plus
15625.
thank you, 15625. And then we have 0.25 times f of 0.5, which is 0.0625. And our last one is 0.25 times f of 0.75, which is 14065. Thank you. So we get all of these values, and then we add them together. So if you have your calculator, please pull it out, crunch those numbers, and when you get a final value, check with your neighbor or have your neighbor look at your answer and see if your neighbor agrees you typed it in correctly. Okay, do I have a second on this number of 0.21875?
Yeah.
Okay, so this number, this is also square units. And And so this is saying that the area under y equals x squared between 0 and 1 is approximately 0.21875 square units. All right, so this number is going to be smaller than the actual area because we left out a bunch of little triangular pieces. So the actual area under y equals x squared is going to be somewhere between this value and the larger value over there. Okay, so this idea that I have written up on the board here, this idea of we want to find the area under a curve, and we're going to do so by taking the interval that we're looking at, breaking it up into little subintervals, and over each subinterval saying the height of our function is constant or flat, and then finding the area by taking the length of the base times the height, adding it to the length of the base times the height, plus the length of the base times the height for each one. When we add up all of those pieces together and come up with an approximation for our area, that's called a Riemann sum. Using subintervals and pretending that y equals f of x is constant over that subinterval, or over each subinterval, using subintervals and pretending that y equals f of x is constant over each subinterval, and then adding the areas of the corresponding rectangles is called a Riemann sum. And Riemann is the name of a mathematician. It's R-I-E-M-A-N-N. All right, so we have one example where we made all the rectangles touch the function on the right-hand side, and then over there we had where the rectangles touch the function on the left-hand side. One was an over-approximation, one was an under-approximation, but there sure as heck was a lot of leftover space that we missed on the under-approximation, and there was a lot of area that we overestimated by on the over-approximation. So this is where we go from the Atari 2600 up to the Nintendo. So we're in the 90s now. So what happened when we went from the Atari 2600 to the NES system was that we had a few more bits per square unit. And so that's what we want to do here. To make a better approximation, we'll use more subintervals. All right, so let's use 8 subintervals. So now we're going to talk about 8-bit graphics. All right, so if I'm going to use 8 subintervals to make some rectangles here, I've got my function f of x equals x squared, and I've got the interval from 0 to 1. And I want to break this up into 8 equal pieces. And in terms of those values along the way, since we're going from 0 to 1, I can figure out the decimals, but it's easier to work with the fractions. We've got an 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and 1. Those are each of our x values. And if I choose to use right-hand rectangles, rectangles where the right-hand corner is going to live on the function, so you sub 8 subintervals with what are called right-hand rectangles, meaning that the right-hand corner is touching the function. Then my picture is going to look something like this. My first rectangle will touch the function above x equals 1/8 and be drawn across. My next one over will touch the function at x is equal to 2/8. And then we've got our third rectangle, and our fourth, and our fifth, and the sixth, and the seventh, and finally the eighth. And if this were a perfect picture, then every single rectangle would look like it had the same width, but different heights. Okay. So when I look at this picture, already if I kind of let my eyes glaze over, already my animation is a little bit better, my cartoon, because there's a little bit more of a curve going on here. It's not quite as blocky as with 4 rectangles. Now I have 8 rectangles. And so if I want to calculate or approximate the area under this curve with the 8 rectangles, then I've got to find the area of 8 rectangles and then add up all those areas. Okay. So I want to encourage you to make that calculation. I'm going to write out the first line, but I'm not going to figure out the rest of the numbers. So what we would say here is, rather than what I had written over here, which is approximate area using left corners and 4 rectangles, rather than writing out all those words, what I'll write out is, I'll write an R for right-hand rectangles with a subscript of 8, because I'm going to use 8 subintervals. So R says right-hand rectangles, and the 8 tells me I'm breaking my interval up into 8 equally spaced pieces. Okay, so if I was really, really excited about this, then, and I am kind of, so I'm going to do it, I would say, okay, well, I've got my width. Well, the width of one of these rectangles is 1/8 for each of those rectangles. And so I've got 1/8 times, now for my first rectangle, the height will be the height above where x is equal to 1/8, so I have 1/8 times f of 1/8. My second rectangle, the width is 1/8, and the height will be the height above 2/8, which is 1/4, if you prefer. My third rectangle will be 1/8 times f of 3/8. Then I've got 1/8 times f of 4/8. So far we've added up 1, 2, 3, 4 rectangles, and we've got 4 more to go. 1/8 times f of 5/8. 1/8 times f of 6/8. 1/8 times f of 7/8. So that last rectangle that I just wrote down was this second to last rectangle in our picture. And our very last one, the width is 1/8, and the height is f of 1. Now for each of these f of 1/8, f of 2/8, I have to know exactly what the name of, or what the formula is for my function. In this case it's x squared, so I'd be plugging in those values into x squared to get the height. So what I have written down all the way across this board here is an example of a Riemann sum. Okay. We've got the width times the height, and we're adding them all up. Now this is a right Riemann sum with 8 subintervals, that's what the R and the 8 are for. If I wanted to do a left Riemann sum, then I would say, with 8 rectangles, I do L8. So over here, this example, if I want to use the shorthand notation, this is L4 because we're using left-hand corners and there are 4 subintervals. Okay, are there any questions or comments about that so far? So I was totally willing to crunch numbers when I had 4 rectangles, and I was semi-happy to at least write out the formula for crunching the numbers for 8 rectangles. But even with this, I didn't really want to bother with all the numbers that went into it. I kind of got tired of that. And in fact, at some point you say, man, this is kind of tedious, writing all of this out. Imagine if we went to the Super NES and we had 16-bit graphics, in which case we'd have to take this interval and break it up into 16 pieces. Or, no, we can't use 32, Nintendo didn't do that, but we could go up to 64. And so suddenly you've got 64 rectangles that you need to calculate the area of, but you're going to get a better approximation than you did with only 4 over there. But this is where computers come in. So I'm going to give you a handout of some pictures where the very first picture, or the pictures on the left-hand side talk about 4 subintervals, and then once you get this, I'll talk about the right-hand side.